I decided that today what I want to do is show you another RISC-V assembly code generation example. So that's what we're going to do. We've got this C code. We're going to walk through and just translate it into RISC-V. At the global scope, I declare an array. Inside of main, let's get rid of that. We just call a fib function, and then we return the last element of this array from main. That's the return value from main. Inside the fib function, we've got a Fibonacci sequence. Takes a pointer to an integer array and the size of the array as the two arguments to the function. Initializes the first two entries to 1. Probably before we do that, we should make sure the array size is that big. So let's just add this. If n is less than 2, return. All this should be just fine. That'll compile, that'll run, that'll return. For the size of 10, should give us 55 as the return value, 10th element of that Fibonacci sequence. So we will begin. We've got this array of 10 integers. As long as you know an int in C is 4 bytes, then you know that you need 40 bytes to represent that array. So we'll declare our array as dot space 40. So that's 40 bytes. That's an array. That's just like this global array here. It's equivalent to what this is here. And then we'll have main. So we'll add our main, and we're going to have fib. Main is going to call fib, and then it's going to return a value. Since it's going to make a function call, we're going to have to save the return address pointer from main so that we can return from main. We adjust the stack pointer by 4 bytes, and then we save the return address register onto the stack at 0 offset. And then we're going to have our fib array 10, and then we'll return array location 9. And this was our prologue. We'll have our epilogue down here where we return. To make our function call, we have to get the arguments into the argument registers. So we need the address of array into A0, and we need the value 10 into A1. Hopefully by now, you already know load address, which is a pseudo instruction. For A0, we're going to load the address of variable array down here into A0 and load immediate into A1 of 10. And then we're going to call fib. Call is a pseudo instruction. We can use it. That's fine. Our fib does not return anything. It's a void. And from our main, we're going to return the array value at location index 9. Each element of the array is 4 bytes. So the 0th element is 0 offset from the address of the array. The first element of the array is at 1 times 4 bytes offset from the start of the array. So we can calculate the address of array 9 using the address of the array first, and then we're going to add to it 9 times 4, because 4 is the size of int, and we want the 9th index. So to calculate 9 times 4, we can do this 2 ways. We can use a multiply operation, mul, and I'll use A1 because it's available. You can use any of the temporary registers here. It's fine. Multiply, and then you need 9 and 4. Of course, this isn't going to work. We have to put 9 and 4 into registers. So T0, 9, T1, 4. So we load immediates T0, 9, and 4. And then we can multiply 9 times 4 into A1, and then add A0, A0, A1. So that's the address of array 0. That's what the address of array is the address of array 0, plus 9 times size of int, which is equivalent to the address of array 9. So we have the address of array 9, then we need the value from that address, and of course, to get the value from an address, use a load word instruction. And we're going to put this into A0, 0 offset from A0. This is one correct way. We're going to come back because we can do this other ways. And we're going to do that in just a minute. A ret instruction is fine there. Oh, before we ret, we have to have our epilogue, load word, return address, and adjust the stack pointer. So you have to adjust the stack pointer in order to allocate space to store something on the stack. You can imagine the stack as some area down here of a bunch of bytes. The 0th byte through the 127th byte. So you have sort of stack 0 through stack 127. You kind of can imagine this as what the memory looks like of this stack space. At the start, the stack pointer points to the end of this. Then you have to subtract from the stack pointer by the amount of space that you want to write something in there. So in order to save the return address in there, you first have to make room in that memory for the return address. So that's what subtracting from the stack pointer does. And then after you load back the return address, and when you're done using that portion of the stack, you add to that stack pointer, and it moves the stack pointer back up to here. And whatever's on the stack is just kind of leftover garbage from that function call. So it's a way of allocating some space. So that's main, fully functional, but we don't have a fib function. So we need to implement our fib function. It might be simpler if I had not just reused all these registers names. So willy-nilly, I guess. T3, that's fine too. And even T4. A little less like confusing about what's storing what, I guess, at any point in time. I'm going to do something just very quick. I'm just going to put a ret in my fib. This is a functional program. It's not very useful, but we should be able to compile it. Good. And we should be able to run it. That's my prologue. If I just step through, I should be able to see the difference. So there's my load address. There's my load immediate. Here's my call for fib. Goes into fib. Fib just returns. Load the address. Load immediate. Load immediate. Here's that multiply instruction. Add, load word. Epilogue now, load word, add, and return. So that's the end of the program. It runs. It doesn't really do anything useful, but I confirmed that it runs. It follows the control flow that I expected for my simple program. Always good to, check that things are working that you think should be working. Of course, the value that's actually in that register right now, we can look at it. Let me see, where's my Windows registers? We can see a value 0. And that's because the simulator is kind to you and initializes memory to zeros. When we implement fib correctly, this will end up being, should be the value 55 in decimal. So fib. Fib is a leaf function. It's not going to make any function calls. We got no function calls here. Since it's a leaf function, I don't have to save the return address register because I'm not going to overwrite the return address register with a function call. And I'm not going to worry about any other registers either. I'm just going to use temporary registers here in the leaf procedure, so I don't have to have anything in my epilogue. I don't actually do anything for this declaration of this variable. This variable is going to live in a register, whatever register I decide to use for my iteration. So the first thing I'm going to do is I'm going to convert this check. If n is less than 2, return. So this is our error handling condition. We are going to put some label, and I'll just make up a label L0 branch over this return if n is greater than or equal to 2. We need a set less than to compare a value to 2. Remember, fib is called fib array and n, so n is in the A1 register. That's our calling convention. So set less than, I'm going to put the result into a temporary register. I want to check if A1 is less than 2. I need to put 2 in a register. I'll put 2 into T1. This is going to be if n is less than 2, then T0 is 1. If n is greater than or equal to 2, then T0 is 0. So this means I want to branch pass this return value when t0 is 0. Range equal t0 x0, which always reads as 0, pass the return. If n is less than 2, t0 is 1, so we're not going to branch past this return, and we'll return. So that implements our little check here. So now I can get down to the business of implementing the rest of this function. Set my array values 0 and 1 to the value 1. I have the address of array is in A0, so I need to write out a 1 to the address of the array index 0. Hopefully you already know, but if not, the address of array is equal to the address of array 0. The array starts at array 0, so the address of an array is the same as the address of the 0th element of the array. So we need a value 1 in a register that we're going to write out to that location. So I put 1 into a temporary register. And now to write to the location of the array, I'm going to use store word instruction. Store word from the register I just put a 1 into. And the location is 0 offset from the array. So that's address of array 0. I want to do array 1 equals 1. I'm going to do this again with the store word. Same register because it's just a 1. This time I'm going to do 4 offset from address of the array. This is because the address of the array plus 4 bytes is equivalent to the address of the array indexed by 1 with 4 byte elements in the array. And integers are 4 bytes. We're using this 4 displacement to get us to the address of array 1. Now I'm going to implement my loop. I equals 2, I less than n, I plus plus. Now remember how we convert for loops into assembly. First we have our init. So init is I equals 2. And now I'm going to assign a register to be I. For this entire loop, I'm going to have I in t0. After the init, I need my loop label. And then at the start of every for loop iteration, we check our condition. If I is less than n, continue, otherwise break. If I is greater than or equal to n, go to done. So we'll have our loop done down here. So we need to compare I to n. N is still in A1, and we're checking I less than n. So set less than. We need another temporary for the result. Actually, before we do this, I'm going to comment this out, and I'm going to run this and make sure this is doing what I think it's doing. So I got a ret. This will eventually be our epilogue. This time I'm just going to run it, reinitialize, then load, and now run. Great. And max, just run to the end. Good deal. So we can see the registers that changed. What we can check is if the array in memory has values 1 and 1 in it. For that, we have to open up our memory window. And then we got to figure out what the address of array is, restart it till I get the address of the array, which is going to be here into A0. So the address of the array here, A0, is at address 278. So now I can go down to 278. All right, so here we have the array 0, array 1, array 2. We can actually see it's still got dirty memory from last time. That's fine. It's doing what we expect it to do. If I change to this value we initialize, if I change that to a 2, looks like when I run it, it sets the memory to 2. Good. This program is doing what I expect it to do for now. So now let's get back to implementing our loop body. This should be A1, not A0. That would not have been, it would not have ever caught the error if I passed a value less than 2 into this. That was always going to be true. So now it's correct. So that was changing this A0 to A1. Now uncomment these things. So I'm back to where I was. If the iterator variable I, which is in t0, is less than n, which is in A1, is I less than n. If I is less than n, then t1 equals 1. Set if less than, otherwise t1 equals 0. If t1 is 0, this is the otherwise, we want to break or go to done. So branch equal t1, x is 0, loop done. So this is our loop conditional, so our I less than n. We're going to put our loop body in here. Just going to put in our comment here. We're going to do that, but before we do that, I'm going to do our loop maintenance increment loop iteration. I++, add I, t0, t0, 1, jump to loop body. There. Now I've got everything except for my loop body. Rerun my simulation, and it should go through the, I guess I can hit play and just see it going through my loop here. And it should go through the loop 10 times. I wasn't really paying attention. I guess we can see our loop iterator in t0, so it's at 9, and it finished. Okay, I'm gonna assume I'm right, even though that's not always the best practice. I have the index I is in t0. So I need to calculate offset in the array of I minus 1, I minus 2, and I. That's going to be the address of the array plus I times 4, the address of the array of I. Address of the array plus I minus 1 times 4 is the array of I minus 1, and so forth. I will do this the straightforward kind of way and just calculate these things exactly as they are written first. This is also equivalent to the address of the array, plus we can distribute I times 4 minus 1 times 4. So the address of the array plus I times 4 minus 4. Similarly, this is going to be equivalent to the address of the array plus I times 4 minus 8. And we've got this as the address of the array plus I times 4. We already have that. So when we have this address of the array times I times 4 here, it's also, you can see it's here, and you can see it's here. So we're just going to calculate that one time into a register. We have the address of the array at A0, so we need A0 plus T0 times 4. Well, T0 times 4 is equivalent to T0 shifted left by 2. Multiplication by a power of 2 is equal to shifting left by the log of that power of 2. All right, this is 2 squared, 4. And so shifting left by the log of 2 squared. Do shift left, logical, immediate. I'll put the result in T1 by 2. Shifted left by 2. And then I will add T1, A0, T1. The address of the array plus I times 4 is now in T1. So I got to keep that around. That's the address where I want to put the result. I want to read from, load from that address to a temporary register minus 4. So this is array I minus 1 because it is address of array plus I times 4 minus 4. That's what we said is array I minus 1. Minus 8 for T1. There we go. That's array I minus 2. Add the 2 together. That's array I minus 1 plus array I minus 2. And store the result to array I. And that's the line of code right there. Done. And that should be my program done. Let's compile it. Run it. Max. Hexadecimal 37. Oh, that is right. Good. So hexadecimal 37 is decimal 55, and that's the Fibonacci sequence element number 9. So this is correct. It's correct. That's fine. I want to go back to here in our main. We can do this better because we're multiplying two integer constant numbers, we don't actually have to do that because we know what 9 times 4 is. Well, we can know what 9 times 4 is. Not very good at math anymore. 36. That's equivalent to what we did, but also we can do that directly to A0. I wanted to show you that you didn't really need to go through calculating the index. If you can calculate the constant numbers, you don't need to execute these instructions. We just calculate the constant offset from the base of the array and put that into our return value, load it, run it, make sure we get 37 hexadecimal again, and it seems to be correct. I'm going to assume it's correct. I think I wanted to show something else. This is okay, this is correct, but it's a little bit inefficient, or it's not as efficient as it could be. I can simplify this because I don't always need to keep reloading values from the array that I previously computed. See, I computed this as part of this program. So, and I computed it not that long ago. Let's say T3 and T2. So I'm going to use T3 and T2 to store in temporaries the calculated value of the last two iterations. 2 iterations ago was T3. This iteration is T2. Down here is where I'm actually going to do it. I'm going to change this into array I is equal to T2 plus T3. T3 equals T2. I want to shift things sort of that way. And T2 equals array I. What I'll be doing is just keeping the most recently calculated values for the array in registers, as well as writing them out into memory. So I still have to calculate the address where I'm going to write to them in memory, but I can keep adding 4 to A0 instead of shifting and adding every single index. Every time I want to go to the next index of the array, I'm going to add 4 to it, add my 2 most recently calculated values. T1 is available to us. T1 equals array I minus 1 plus array I minus 2. Store word 0, and then move T3 gets T2, and T2 gets T1. That's array I. And now I don't need these instructions. I don't load word those anymore because I'm keeping track of them. I do it with 2 adds, a store, and 2 move instructions instead of a shift and add, 2 loads, and add, and a store. It's 6 instructions versus 5 instructions, so it's fewer instructions. It's also fewer memory instructions, which generally are going to be more expensive. Well, let's run this and make sure it works. We get 0x37. I feel confident this is correct. If I go over to my core, I can see it was 102 cycles. 102 cycles for this version. I can go back to the other version. Should probably have saved them as 2 different files. That would have been smart. Yeah, right here. Right there. There. Really should have done it in 2 different files. There we go. So that worked, and it's 107 cycles, so only 5 cycles different, not a huge difference. That's because we just shaped 1 instruction per loop. But it's going to make a pretty substantial difference in terms of loads and stores, and the larger your loop is. But I mostly just wanted to show it to you as kind of an example that you can calculate the indices of arrays by multiplication. You can typically calculate the indices of the arrays by shifts and adds. Well, it's multiplication, so of course you can do it by shifts and adds, but it's like a straightforward shift and add because it's a power of 2 usually. And that you could think carefully about how you reuse values that your program calculates. Take this whole chunk of code and I'll share it with you. This version, look back at this video to figure out what to uncomment or comment.